Operating an electric arc underwater instantly vaporizes the surrounding water, creating a steam bubble known as the gas cavity. This cavity is not pure steam. It contains highly flammable hydrogen and oxygen generated by the dissociation of water molecules due to the intense heat. The welder is essentially maintaining a stable arc within a potentially explosive gas pocket while managing currents up to 500 amperes. Increased hydrostatic pressure constricts the arc column, significantly raising the arc voltage required to sustain the plasma. This constriction increases the current density and temperature within the arc core, demanding specialized power sources designed to compensate for the variable impedance of the hyperbaric environment. The primary metallurgical challenge in underwater welding is the rapid cooling rate, or quenching, caused by the surrounding water mass. This rapid quench prevents the slow, controlled cooling necessary for optimal grain structure. In wet welding, the weld metal cools so quickly that it often forms martensite, a hard and brittle microstructure with low ductility. Furthermore, the high hydrogen content trapped in the weld metal leads directly to hydrogen-induced cracking, also known as hydrogen embrittlement. This severely limits the application of wet welds to non-critical structures or temporary repairs where high fatigue resistance is not required. Wet welding predominantly utilizes the shielded metal arc welding process, requiring specialized waterproof electrodes with potassium titanate flux coatings. These coatings are designed to stabilize the arc and minimize hydrogen pickup. The electrode coating must be highly resistant to water penetration to prevent short circuits and maintain flux integrity. Despite these specialized materials, the resulting weld quality is inherently inferior to surface welds due to the rapid cooling and porosity issues. American Welding Society standards typically restrict wet welds to depths above 100 meters and mandate specific mechanical testing protocols to verify minimum tensile strength and ductility requirements. For critical structural repairs requiring surface-level quality, hyperbaric welding is performed inside a dry habitat. This sealed chamber, pressurized to match the ambient water depth, displaces the water and allows the use of standard welding processes like gas tungsten arc welding or flux core arc welding. The habitat atmosphere is carefully controlled, typically using a helium and oxygen mixture known as Heliox to mitigate the physiological effects of nitrogen narcosis and reduce breathing resistance at depth. Even in a dry environment, the increased pressure affects the metal transfer mode and arc stability, necessitating precise calibration of wire feed speed and voltage settings. The primary physiological risks for saturation divers performing hyperbaric welding include decompression sickness, nitrogen narcosis, and oxygen toxicity. Decompression sickness, or the bends, occurs when inert gases dissolved in the body tissues form bubbles during ascent, requiring strict adherence to decompression tables or saturation techniques. Saturation diving involves keeping divers at storage depth for days or weeks, minimizing the number of required decompression cycles. Nitrogen narcosis impairs cognitive function below 30 meters, which is why helium substitution is mandatory for deep welding operations to maintain diver safety and precision. The cost structure of hyperbaric welding is dominated by mobilization and operational expenses, not material costs. Deploying a saturation diving spread, which includes the diving support vessel, saturation system, habitat, and a specialized team of tenders and welders, involve mobilization costs often exceeding $1 million. Daily operational costs for a fully saturation system frequently surpass $100,000. This high fixed cost necessitates extreme efficiency in project execution. Weather delays and unforeseen technical issues directly translate into massive financial losses, making detailed risk assessment and contingency planning essential for profitability. The demand for underwater welding services is driven primarily by the maintenance and repair of aging offshore energy infrastructure. Oil and gas pipelines, platform jackets, and subsea risers require periodic inspection and repair to maintain structural integrity and regulatory compliance. The increasing depth of energy exploration pushes the limits of human diving capability, favoring advanced saturation techniques and potentially robotic solutions. Infrastructure projects such as bridge pier repairs and harbor facility maintenance also constitute a significant, though often shallower, segment of the market. Regulatory compliance is governed by international bodies and national standards, with the American Welding Society D3.5M specification being a key industry benchmark for underwater welding. This standard dictates the qualification procedures for welders, the acceptable range of metallurgical properties for the weldment, and the non-destructive testing methods required. Welders must pass specific performance qualification tests, often conducted in hyperbaric chambers simulating operational depth, to certify their ability to produce sound welds under pressure. Failure to adhere to these standards results in immediate project shutdown and significant legal liability. The future of subsea repair is moving towards automation to mitigate human risk and extend operational depth. Remotely operated vehicles, or ROVs, are increasingly being equipped with advanced manipulation systems capable of performing complex tasks. Emerging technologies like friction stir welding and laser welding are being adapted for subsea application, offering potential advantages in metallurgical quality and speed compared to traditional arc welding. These automated systems promise to reduce the reliance on expensive saturation diving spreads, potentially lowering operational costs and opening up deeper repair markets previously inaccessible to human intervention.